welcome. Let's do more related rate problems. A stone is dropped into a calm body of water, causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Right? So we have this circular body of water, right? We have a body of water, and what matters is that the ripples are circles, right? And so the radius of the outer ripple is increasing at a rate of 1 foot per second, right? So that gives us some information. When the radius is 4 feet, right? So we're looking for when r equals 4. At what rate is the total area of the water changing? So identify all variables involved in the problem. Right? So we have a radius. Right? Radius equals 4. And I almost forgot, A is area. I think I tend to forget to identify the variable that's going to give us our equation because we're looking at total area. Identify which, if any, of the variables in the problem remain constant. Right? Well, nothing's going to be remaining constant here. And actually, let me put r equals radius. Right? So we're interested, though, when r is 4. It's not remaining constant, but we're interested when the radius is 4. So here, none of the variables are constant. Right? As the radius increases, the area is going to increase. So none. Identify the rates which are given and the rate we wish to find. Right? So we are given dr dt. It is positive, right? Because if you drop a pebble, right, the ripples are increasing. So dr dt is 1 foot per second. dA dt is what we're looking for. Right, so we'll write an equation that relates area and radius. Of course, it's the formula for the area of a circle. I'm just going to move that up so I have some space there. I'm not going to read through that each time. I read through it once. So we have area of a circle is pi r squared. All right, so now I'm just going to continue, right, rather than waste all that space. All right, so now we have our equation. Right, once we have our equation, there are no constants in this. Right, everything is changing. So we're going to take the derivative with respect to time. So we have dA dt equals, right, pi is a coefficient, so that's just going to be pi times 2, and then the radius the exponent will decrease by 1. And then, of course, with respect to time. Let's clean that up a little bit. So dA dt equals 2 pi r dr dt. We have already got all of our, this was 5, by the way, and this was 6. And we've got everything isolated. We've got dA dt isolated. All we have to do now, this will be 7, is just plug in. I just kind of have to do those things one after the other. But here on the side, you've got exactly the steps and what you're actually doing. All right, so we're looking for dA dt. 2 pi, the radius is 4, right? Just make sure I didn't forget. Yep, and the dr dt is 1. So dA dt is going to be 8 pi, was it centimeters? All right, one of us has to really pay attention to the units, Pete. 8 pi feet squared per second. I can't see the problem anymore once I scroll down. So I'm going to have to look back up or make sure I pay attention. All right, and that's all there is to it. So the area, if the radius is increased, let's put our final answer here. Let's put our explanation. So the area of the, let's call it the disturbed area. The disturbed area, since that's the way they labeled it, is increasing at a rate of 8 pi feet squared per second when the radius is 4 feet. And there we go. That's that problem. All right, so come back and we'll do another one. Thanks for watching. Bye for now.